Right now, you might be holding something completely ordinary. A pebble from your driveway. A tiny speck of dust stuck to your laptop screen. Or maybe nothing at all. But the fact you're surrounded by air means you're still in constant contact with billions of tiny particles. They're everywhere. You breathe them in. You exhale them out. You brush them off your clothes without thinking. And almost all of them are boring. But not all of them. Because hidden among the trillions of ordinary particles in your life, there could be one that, if you looked close enough, could take you on a journey. Not metaphorically, not imaginatively, but chemically back to a time before the sun even existed. First, let's unpack what that means. The sun is 4.6 billion years old. That's big. But the universe is 13.8 billion years old. So there's this 9 billion year stretch of cosmic history before a solar system even showed up. A lot happened in that time. The first stars ignited, galaxies formed, stars died in massive explosions, and entirely new generations of stars were born from their ashes. And it's that ashes part, or stellar ashes, that matters here. Because when stars die, they don't just vanish. They shed. They blow their guts into space in the form of carbon, oxygen, iron, and even gold. And those atoms drift around until gravity pulls them into new clouds of gas and dust. Those clouds eventually collapse into new stars and new planets, and sometimes us. Let's start with something simple, like carbon. You're made of it. Your dog is made of it. The plastic around your phone is made of it. But here's the twist. Carbon comes in different flavors called isotopes. Same number of protons, which is 6 for carbon, but different numbers of neutrons. Carbon 12, 6 neutrons. Carbon 13, 7. Carbon 14, 8. And unstable, so it decays over time. Now, this difference might seem small, like swapping one Lego brick for another the same color but slightly heavier. But on the scale of atomic chemistry, that tiny difference is huge. It changes how carbon forms, how it reacts, and, crucially, where it comes from. In the early 1960s, a chemist named Edward Anders was studying meteorites, not because he expected to find alien life or some secret message, but because meteorites are basically time capsules. Most of them formed around the same time as the planets, meaning if you study them, you can study the early solar system. But in 1962, Anders and his colleagues found something odd. Inside certain meteorites were tiny mineral grains, microscopic, smaller than the width of a human hair, that had isotope ratios completely different from anything in the solar system. These weren't just slightly unusual. They were impossible. The only way to explain them was that they formed somewhere else, around other stars, before our solar system even existed. So how do you figure out where a grain of dust came from? It's not like it comes with a made in a red giant sticker. The trick is to compare isotope ratios. Every type of star acts like a different kitchen, mixing elements in its own unique recipe. A red giant might make lots of carbon, 13. A supernova might produce unusual silicon isotopes. By measuring the ratios inside a grain, you can match them to the recipe of the star that made it. It's like tasting a dish and saying, "Yep, this is definitely from Grandma's kitchen, 10 billion years ago, halfway across the galaxy." And speaking of recipes, there are two main ways stars cook up heavy elements. The slow neutron capture process, the S process. Imagine stacking Lego bricks slowly, one by one, letting each one click securely before adding the next. This happens in older, swelling stars called red giants. It takes thousands of years, but it makes elements heavier than iron, like strontium and barium. The rapid neutron capture process, the R process. This one is chaos. It's like trying to stack Legos during an earthquake while someone's throwing bricks at you at near light speed. This happens in extreme events, supernovae and neutron star mergers. In less than a second, atomic nuclei get blasted with neutrons so fast they don't have time to decay between captures, making some of the heaviest elements in the universe like gold, platinum, and uranium. Speaking of neutron star mergers, in 2017, astronomers detected one. Not visually at first, but through ripples in space-time, gravitational waves, picked up by LIGO and Virgo. The numbers are absurd. A neutron star is so dense that a teaspoon would weigh 1 billion tons. That's like squeezing every human on Earth into a single sugar cube. When two of these collide, the energy released is beyond comprehension. Trillions of times more powerful than all the nuclear weapons on Earth detonating at once. The debris from that event? Rich in heavy elements, some of which will drift for millions, even billions of years until they join a new solar system. So, back to that boring pebble you picked up earlier. If it's a meteorite, and if you looked inside, really inside, at the tiniest grains, you might find a few that predate the sun. Grains that formed in the final moments of a dying star, traveled alone through interstellar space for eons, got trapped in the cloud that became our solar system, survived planetary formation, survived billions of years of impacts, and finally landed here.